for staying for until the last talk. What I'd like to talk about today is some aspects of the Hubble tension, paying more attention on some issues that have not perhaps been stressed so much in previous talks or in the literature. So let me start saying that we live in exciting times in the sense that there have been so many tensions gathered during the last few years, so it's quite likely that we live in an era where there is a new shift of a cosmological model. There will be, at least in the near future, one. So in this context, it's interesting to see what were the requirements in the past that led to this kind of transition, to shift of cosmological model. And there are two main ingredients. One is the data. We need to have new data which are inconsistent with the previous model. And the second and most important, actually, I would say, is we need to have a simple, generic model which will replace the previous one. So in most previous cases where we had a replacement of a cosmological model by a new one, we had both of these ingredients. And let me very briefly go through them. The first one is the oldest cosmological model, which is the Ptolemy geocentric system, where it was believed that the Earth is in the center of the universe. Later on, data which were based on the retrograde motion of planets and various other data came to replace this with the heliocentric model. So we had a simple model and data, which made this replacement. Now, later models also followed the same principle. We had this heliocentric to the infinite universe, and we had the infinite static universe of Einstein replaced later on the infinite universe. And then again we had data, and of course in that case we had also theory. Later on we had the static universe replaced by the expanding universe, which was based also on data on the Hubble law, Hubble data. And we also had later on the introduction of inflation using the CMB and the Big Bang model. We had the introduction of dark matter later on as a new degree of freedom. And in 1990s, we had the introduction of lambda CDM based on new data, and of course here by the existence of the new data which introduced this necessity. Now the important thing is that we now are in this next stage, which indicates that we have lots of tensions, in fact, many more tensions than before. And the reason that lambda CDM remains as the standard model right now is because we actually don't have a model, a simple and generic model which will replace it. In fact, we have the opposite problem. We have too many data, which is essentially like a noise of tensions which do not point to a clear direction. However, it's clear that we need something else, and that's one of the issues, that one needs to use the data, the tensions, to actually find a new model. And here I just show our review, where we'll try to group and show all these tensions in a single unified manner, trying to perhaps use it as a guide for the next model. Now let me continue with just showing you this usual graph we have shown many times so far, which is the growth tension and the Hubble tension, which are perhaps the most well-known tensions, even though not the most strongest ones. And I will focus mostly on the Hubble tension, and you can see here that in fact what one sees is what has the early time data, the early time measurements, and the late time measurements, which indicate this tension of about 5 sigma, at least with the particular data here. Now, this is a very profound issue, profound picture. If one looks a bit more carefully, it's not really the local measurements versus the early measurements which are in tension. What is actually happening, if you go to split these local measurements in some more detail, this part here, and split them in two groups. One group would be the one-step measurements, which do not make use of the distance ladder, and the other group would be the measurements of the distance ladder. There you see a somewhat different picture, which shows that it's not really the late measurements which are in tension with the CMB. Here you see one-step selection, a compilation of one-step methods, which are, most of them are local, do not use the sound horizon, and measure the Hubble parameters. And you see that all these local measurements, these are local except from this T-quality standard ruler, come essentially, most of them come to a conclusion of a value of the Hubble constant which is more consistent with the early time, with the CMB. And so this split between early time and late time models may not be a very successful way of thinking of things, but it's perhaps more useful to think of it as a split between methods that use distance ladder and methods that do not use distance ladder, which include, of course, CMB and all these local approaches, except, of course, from these two, which are, this has been revised by the TD Cosmo plus the 33 additional lenses, and also this mega measures measurement. And of course, there are some others too, but I just want to point out there are many local measurements which are consistent with the CMB. Now, the other group, of course, as I said, is the distance ladder. Now, all these measurements that you see here are completely distinct, and they all use distance ladder approach, which means they calibrate at astrophysically close distances, and then they measure, assume that the parameters of calibrations are the same in the Hubble flow, and then they make the measurement in the Hubble flow for the Hubble constant. And you see that essentially all of them are in full agreement, or are more or less in agreement, to a value which is in tension with the CMB. So the question is, could it be some systematic in these measurements which leads to this result? And if there was a systematic, of course, it would be hard to imagine it's the same for all these independent approaches. And so one can see, could we be missing something with all local calibrators? And what would be something that would be similar for all local calibrators? It would probably have to be some kind of new physics, local physics, which is common to all these methods. So this is an approach that I will try to support in part of today's talk. But let me first discuss a little bit the Hubble crisis approaches, which is basically the question as to why is this Hubble expansion history, this h of z calibrated with the sound horizon, does not hit this point here, which is the local measurement of, which is the Moscow training by the Cepheid SUS data, and there are the other local distance ladder measurements. Now, there are various ways to make these two agree. One way is to find a way to take this point down so that you can make it come down to the value of the CMB prediction with lambda CDM plus the CMB. And this could be involved, for example, looking for some systematics in the data, or looking for, as I said, to some local physics. Why would the supernovae of the calibrators be different from the supernova in the Hubble flow? What could be the cause that would make them different? One would be some systematic. For example, we didn't measure the local supernova in a proper way, or there was some real physics change at redshifts between 0 and 0.01. In this case, one would move the blue point down, because in that case the supernova would be calibrated in the wrong way, and so we would have to correct for this systematic or the new physics to bring this point down. The second approach is to change the sound horizon scale, but in that case you would also have to change the time of equal matter radiation horizon, because this is also used as a calibrator. So we have two early time calibrators. One is the sound horizon, and the other is the time of equal matter radiation through the matter power spectrum, which is measured. So if you find a model or a way to change both of these standard rulers in a consistent manner, then you could actually shift this line up, and it will become consistent with the local measurement. The third approach is to deform this line through some, let's say, late dark energy or some kind of various interacting dark energy models or various other models, which change the history, expansion history, to another form, which is consistent with the CMB sound horizon and also is consistent with this point, but after a deformation of this, proper deformation of this Hubble expansion theory. Now, these models have various problems, and in fact, the problem they have is that, first of all, they are not consistent very much with the various baryon acoustic oscillation and growth measurements. And this is because what seems to be a single point here is not really a single point, because you have other supernovae which probe higher redshift. So in fact, this point here is, if you use this calibration here of local measurements, it's a series of points which has, well, this is a artist's view, it's not a real data here. So there's a series of points which have to also be taken into account in conjunction with this baryon-acoustic oscillation and other distance moduli of baryon-acoustic oscillations, which should be taken into account with respect to this. And it's very hard to make a deformation which will be consistent with both these points and with these bow points and the other bow points which also have the distance moduli in them. So one such model, of course, which is interesting, and that's why I'm pointing it right now here, is that the lambda CDM model, which makes the transition of the Hubble expansion history at some redshift about 0.2. You see it jumps up and goes up and fits, tries to fit at least the supernova calibrated with the Cepheids. And so of course it misses many of the bow points here, as you can see, even though the errors are bigger there for the bow points. So in fact, it creates not such a serious problem. You see here that from a paper recently on this point, on this model, you see here that we have the absolute magnitude of supernovae being somewhat bigger than what is measured by the SUSE measurement. So it does seem to fit the data, but it has to actually increase somehow the absolute magnitude of supernovae. So this is a successful model, but still it has a problem with fitting both the bow and the supernova data. And we are doing some work on that, which seems to have good features with respect to the growth tension, because it increases the growth at higher redshift and decreases at lower redshift. So Osgur probably will talk about this in his talk. And here you see a little bit more clearly the problem. Let me go in a paper that we have recently shown. This is the residual distance moduli as obtained with respect to the Planck lambda CDM. These are the bow data. This is the Bint Pantheon Plus data. And you see that if you try to interpolate with a deformation model, it's hard to fit both the supernova and the bow points because they are inconsistent. You have bow points in supernova which are not consistent with each other, so they cannot be fit by any deformation. The blue points, which are the bow points, are simply... Now, these bands are the best fit Pantheon Plus model, lambda CDM, and this is the corresponding point of bow. You see that they are different because we have different calibrators. And we have to take it into account when we measure the luminosity, these luminosity distances. Anyway, now the deformation models do not really do a very good job cannot do a good job in fitting both bounds and supernova data because simply these are inconsistent and you cannot pass a line through both the blue points and the red points. And that can be shown also by splitting this bow and Pantheon data into bins, in a low redshift bin and a high redshift bin, and you see there is inconsistency between in the lower redshift bin and also in the high redshift bin it's actually a little bit better, but still we have this problem in the low redshifts, which creates this issue with... Now, the early time models also have some issues. Here is a paper by Sani Vanosi published in this special issue we had with Eleonora and Jackson, and which shows that there are in fact problems. There are several problems with with early time models, and in fact one of them, which I think is quite important, it has also to fit. It has to change not only the decoupling, the horizon of decoupling, but also the horizon at the time of fecal matter and radiation, and that creates a problem in general with respect to fulfilling these two. Now, the other problem of this class of models is that they cannot really fully resolve these tensions. You see, the Hubble parameter that they lead to is marginally consistent with the SUSE measurements. So, even if you change the sound horizon with these are various models which change the sound horizon. This is, for example, the early dark energy. This is the dark radiation, various modified gravity, and various other attempts, which do the same thing, and you see that none of them actually fully resolves the Hubble tension, but improves it. So that's an issue to consider for this class of models. And so what remains is to look at the local physics case, and this would involve assuming that the supernova in the Hubble flow are different from the supernova where the calibrators exist in the same galaxies. And so we have to assume a transition, a change of the absolute magnitude of supernova in the Hubble flow, which is measured by this, with respect to the CMB Hubble parameter, with respect to the one measured directly using calibrators. So this class of models one can actually consider and see if the tension resolved in this class of models. And we have redone the SUS analysis using two different approaches. We have derived the distances to the Cepheid hosts of galaxies within the local distances, and did it in two ways. One way was to fix all the calibration parameters and the supernova absolute magnitude, as was done by the SUS collaboration. We reanalyzed this data, and we find, of course, that the calibrators show the distance moduli for these galaxies are in fact consistent with the SUS assumption. But if you allow for a change, you do the same analysis, allowing for a change of the absolute magnitude of the supernova, you see that the two furthest hosts seem to go spontaneously to go to a lower value of MB and become consistent with the CMB calibrators, the Sound Horizon Inverse Distance Ladder calibrator. So that's an indication that maybe there is some interesting physics happening here, which one may want to consider by more detailed study of what these calibrators tell us for the supernova within the local, within the Cepheid hosts. Now, anyway, I'm just showing here how we did this analysis, where we actually we did the full calibrator, the full analysis of fitting the calibration parameters, the absolute magnitude of the intercept of the Cepheids, period luminosity relations. This is the BW, the parameter which period luminosity slope parameter. This is the metallicity parameter, and these are the absolute magnitude of supernovae, and this is the Hubble flow supernova, the corresponding. Okay. So anyway, I don't have time to go further with this. I will just show that this can be done actually, this analysis, by either assuming a fixed value of MB or allowing for two values of MB. And one can actually do the analysis and show, if you allow two values of MB, of the absolute magnitude of supernova, one can obtain various generalized analyses. Here I show the one that we have published a couple of years ago, which shows that if you allow for this change, then the Hubble, this change of magnitude, without imposing any information about the CMB measurement, spontaneously the absolute magnitude of supernova changes at this is larger than about 48 megaparsecs, and we get an H node which is close to what the CMB says. Now, there are other groups who have done similar analysis, not exactly in the same spirit as ours. Here you see another which was done by Rutschka, and it's in preparation. We are also looking at this, which also assumed both MB and MW to change, to allow it to change at a given distance. And also here is the corresponding analysis by Radoslav Wojtak, who allowed for the color parameter to change at a given distance. So he looked at the color parameter for the supernova for the local supernova in Cepheid hosts with respect to the supernovae these are the calibrated supernova, and these are the Vita for the supernova in the Hubble flow, and found that they are not very consistent. In fact, there is a small chance that they have the same value. There seems to be a change in value. So this is an issue which needs further investigation. In fact, if he assumes this value of CRF here, this parameter here, one can also change the Hubble parameter over here. So anyway, that's all I had to say. These are the conclusions. Thank you for your attention.
Thank you for the interesting talk. I generally do agree with your conclusion because there is a growing body of evidence for progenitor age bias in supernova cosmology. And we have several posters on that, so soon you will see them. And we do predict some systematic difference in terms of progenitor age between the calibrated sample and the Hubble flow sample. So this can alleviate the Hubble tension, if not solve the tension.
Yeah, thank you for the comment. I mean, my message was that one should look at these things more carefully. Not just assume that everything that is given is definitely fully checked. So one should check for these variations to look at possible issues in the analysis, in the calibration analysis.
Thanks, Leandros. Is there something you can tell us about what in the data is driving this shift that you're seeing? It just seems to appear mysteriously. Is there?
Well, there are two hosts which are the highest distance, which seem to induce this kind of change. What we did, we just reanalyzed this. We did the full analysis. We just allowed for a change, as you can see here, at various distances. Now, if you, for example, allow for a change at a distance, let's say 30 megaparsec, then you see no change in the Hubble constant. More or less, the Hubble constant remains the same. But at this point, when we reach this point, we found that the data they ask us to make they give a much better fit if you have this change of MB. It prefers to have an MB larger, smaller than the MB smaller, without knowing anything about the CMB. So there is no input about the CMB here, it's just the data. Now the problem is that there are only two hosts there. There are only two Cepheid hosts, so the error bars are big. If it happened in some lower redshift, where we had more hosts on the larger bin, we would see smaller error bars. Now if you also put the CMB data there, the inverse distance ladder, then the errors become extremely small. You have a huge tension, a huge change between the two MB. So in that case, it becomes much more favorable to have this change. But we wanted to make it blind from the CMB. Just ask the data themselves. Do they like to have a change in MB? And they asked us, yes. And the point is that here, we didn't allow MW to change. For example, the intercept of the period luminosity relation was kept fixed. In a realistic physics change, we should have allowed also this to change, because we want to have a small number of parameters. We didn't want to put many parameters there. But Ruchika, recently in a study, also allowed that. And in that case, as you can see here, then there is a much better, in this paper here, there is a much different, smaller error bars, and you see that there is a minus 19.2 and a minus 19.5 for the MB, and the H node also changes very much, because in a transition, you expect more than one parameter to change. So that's why we only allowed one parameter to change. But exactly what data causes this, what data point, it's not clear, because it's not. We didn't really. We could look at this, but it's an interesting point to see exactly what property of the data caused that.
If I may ask a question myself here. So, okay, you talk about a transition, but if you think about physically, either thinking about galaxy evolution or a white dwarf which is exploding, the time lapse since the last 50 megaparsecs here is very, very small. So you're really thinking of a physical transition, or are you thinking that selection effects, or what is your?
Okay, I'm not going to say what is the cause of that. In my mind, it would be a physical transition, and now we don't know exactly what. For example, in this work by Ruchika, she assumed a gravitational transition, which is about 4% change of the gravitational constant, and that would lead to these results. But of course, I'm not saying that this is the only way to do that. But since it's common to all distance ladder measurements, the only way to make it common and consistent among all those different measurements is to have a real physics change. If you have a systematic, you may say, why this systematic happens here and not there? Why does it happen to all of them at the same time?
Thank you, Leandros, for the very nice presentation. Well, my question is related to yours. What is the physical process which drives the transition from?
Yeah, that's a good question, of course. I don't have a fixed answer in that. The simplest assumption to make is that there is a small change in the gravitational constant, about 4%, for example, or 5% change of the gravitational constant, which would immediately induce a change in the physics of the supernova themselves, and also of all other astrophysical calibrators and the Cepheid. So this change would be very hard to detect because, well, it would affect different kinds of objects in similar way. So in principle, this is what I have in mind. Of course, one can think of some other systematic which affects all the calibrators in a similar way. I'm not going to insist that this is the only way you can see this kind of transition, but it's one I would say, natural possibility. I mean, to my mind, it's more interesting theoretically because it would open a very major window for theoretical models if it goes true. And we have thought about some possibilities about that. But it's interesting to actually test on astrophysical data, other data also, to see if there are hints. In fact, we looked at the Thule-Fisher relation, and we find some hints of these effects. Even though the error bars are very big, it's worth to look at this possibility also.
Thank you.
Let's thank Leandros again.